So I am extremely pleased to have Karthyek speak here. So Karthyek is an assistant professor in Singapore University of Technology and Design. His research interests lie in applied probability optimization under uncertainty, and with a focus on developing stochastic models and methods for optimization under limited data resources. Prior to joining SUTD, he was a postdoctoral researcher at Columbia University and IOR department, and he obtained his PhD from Tata Institute of Fundamental Research in Mumbai. He has won awards from 2021 Informs Junior Faculty Forum Paper Competition and 2019 WSC Best Paper Award. So he also serves as an associate editor for stochastic systems. So Karthyek is known for his work on distributionally robust optimization, bringing distributionally robust optimization to applied probability problems, and also rare event analysis. So without further ado, let me give the floor to Karthyek. Karthyek, please go ahead.
Thanks very much, Han, for the kind introduction. I would also like to begin by thanking the seminar organizers for running this fantastic seminar series and for providing me the opportunity to speak here. It's a privilege to be speaking here. Thank you for joining today. Today, I'll be presenting a new approach towards importance sampling. Traditionally, when it comes to tail estimation or risk estimation, we ask for explicit prescriptions for change of measures. But that approach quickly turns out to be not scalable for difficult tasks. So once I go beyond the traditional setup of sums of random variables, it becomes quickly not scalable. So, and this has been a difficulty plaguing the use of importance sampling in difficult problems for a while. And with this work, we hope to take a crack in that, to make importance sampling scalable for difficult or for complex tail estimation tasks. And the approach is quite radically different from the traditional approaches that we see in the literature. And I'm delighted to share that with you today. So this is joint work with Anand Dio, who did this work as part of his PhD thesis while working with me. And let me get started now. Today, there is a great interest, this day and age, there is great interest in leveraging every bit of data, extracting every juice out of the data to make effective decisions. Here I have a data set of mortgage modeling, where you have this is US mortgage model data, mortgage data set. So here we have a pool of 120 million loans with 294 features. Many of them are common national level economic features such as GDP, unemployment rate, etc. And some of them are county level features. Some of them are even zip code level features. And many are loan level features such as person's individual FICO score, etc. So we have such a huge, rich data set. And it's has been well known that the best way to make the most out of such data sets is to develop to build models which take all the inputs into account and make good out of sample predictions. So here for example, for such a data set, a recent paper by Sirignano, Sadhwani, and Gezeke, they show that you can obtain extremely superior out of sample performance compared to the traditional methods by using a 5-layer ReLU neural network. So we have to extract the most juice out of such data sets. We have started developing complex models, and we complicated, sophisticated predictors. We employ them, we plug in them in our models, and then have to work with them. Now, given such a model, equipped with such a model, for decision making, I would be given a portfolio model like this, using 294 features, I'll be naturally asked with tasks such as how do you assess the likelihood of large portfolio losses, or given a loan pool, how do you select loans whose risk is low? Risk could be, for example, the excess losses are low while meeting a target return. So how do you make such decisions on such complicated data sets? So So another example that I would like to stress here is like we have power distribution networks, like they kind of operate on like we have smart grids, the idea of smart grids, where like sensors collect data throughout the day in different parts of the power grid. And we have started developing this feature-based decision rules, which map these predictive forecasts into prescriptions, how to generate and how to transmit. We kind of have started having these feature-based decision rules. These are again complicated decision rules which may be making use of some random forest or neural network type of predictors. When you plug them in your model and you want to kind of do some downstream estimation or optimization. For example, you want to evaluate for a given predictive prescription, how do you kind of evaluate the outage risk? Or how do you kind of identify a decision rule which minimizes the total operational expenses while controlling the probability of outage risk? So there are these questions like where we kind of inevitably have to, where risk is important, we have to make decisions which are risk minimizing. We have to have a control on risks, but we also kind of like have to work with sophisticated predictors and models. The idea of like controlling risk and managing risk kind of resonates now at this in the last 2-3 years, where the macroeconomic scenarios have kind of seen a lot of upheavals, the shortages, like the high interest rates, labor shortages, energy shock, all of them have kind of like contributed to price volatile prices, like uncertain operations, uncertain supplies, uncertain demands, and so on. So I think like in this day and age, like given all that we have been witnessing the last few years, managing risk has kind of like again like kind of started coming back into the front of the business managers and like risk management teams. So like the topic that I kind of like want to be touching today is like trading off risk and return, like estimating risk and trading off risk and return. And that's a common theme in like kind of like if I want to run a operation like which offers high service guarantees, or if I'm doing a quantitative risk management, like kind of like for a portfolio, or if I'm kind of if I'm running a cyber physical system, and if I want to make sure that, like, for example, something like an autonomous vehicle or a cyber or a transmission grid, I want to ensure safety constraints. All of them kind of like evaluate to some form of, all of them require evaluating tail risks, as well as kind of making effective decisions which minimize the tail risk. So the subject I'll be touching upon today will be this trading off risk and return, particularly evaluating risk and using it to solve optimization problems. Now, like, without further ado, let me introduce the problem we are considering. So here L of X denotes loss or cost when where X is an underlying random vector, like which kind of like quantifies all the uncertainty in the problem. So X models all the uncertainty in the problem. Is a random vector, potentially of multiple dimensions. An example here is like we have a shortest path problem where you have you want to go from route from source to destination, and you kind of like look at the cheapest path. So the cost of traversing edge could be random, and if you look kind of evaluate the linear program like over the shortest path polytope, like you get the cheapest cost. So that's an example of what L of C could be. Or L of C could just be a simple linear combination of C's, but like this is an example. It can be value of an LP, for example. Or like I can like even kind of like consider a little more sophisticated example where I have a contextual shortest path problem. Here Cij is a function of two things. It depends on two things. One, side information S and some observed uncertainty. And I have a predictive prescription. Like, so when I'm making the prescription, I know like the side information. So I can make my decisions as a function of, I can decide my route, the route traversed, as a function of like the side information that is given. So I kind of like write it as theta as a function of S, and I can look at the cost as a function of theta, and theta could be coming out of, for example, a random forest predictor. So let's say I kind of like have this contextual shortest path problem. Then I want to kind of like evaluate the risk in evaluating in kind of like plugging in this predictive prescription. If I use this predictive prescription repeatedly, how will my excess losses fare? What is the risk in it? Now, like, so that abstract task that we are considering here is given a loss like this. And if you have access to evaluation queries of L, I may or may not know the closed form expression for L. In simple problems, I may know the closed form expression, but in complicated problems, it may not be practical to write down closed form expressions. So I kind of have access to queries of L, also the probability density of F. Like I just assume queries to loss as well as the density of X. And then the task that we are interested in is like, how do you evaluate the probability of losses being large. In other words, like you want to estimate the distribution tail of L of X. Once you kind of get hold of the tail, it's also natural to ask, can you evaluate value at risk? Can you estimate value at risk, which is like tail quantiles? Or can you evaluate conditional value at risk or expected shortfall, like which is kind of averaging the largest fraction of largest beta fraction of the scenarios losses if you get the conditional value at risk. So naturally, we are interested in these tail estimation tasks. Now, once we kind of like get hold of the tail estimation properly, we can also think of optimization. So here I have a loss which depends on both the uncertainty as well as the decision. So theta could be used to denote a decision choice here. And you want to consider a formulation which trades off risk with return. So rho could be thought of as a risk measure, such as C bar, conditional value at risk, which is nothing but evaluating the average loss over the largest beta fraction of the scenarios. So here you have like X is a random vector, which takes value in like multiple dimensions. And we have a small like kind of extreme set, like which is shaded in red. And if I kind of look at the distribution of L of theta of X, then like I just look at the largest beta fraction of the largest, which is the shaded one in the red, in the right hand side here. Okay. So now given a tail estimation task like this, or given a tail optimization task like this, what are the common approaches? How do people approach it? The most common and the most reliable and the most used approach is just the simple sample average approximation, or naive Monte Carlo or crude Monte Carlo, regardless of however we may call it. Simple, I just take averages from I obtain samples and I kind of like just take the average to compute the tail, and then use the average to compute value at risk, quantile, or conditional value at risk, and so on. But the task is simple. I just like do nothing fancy. I just do a naive Monte Carlo. I obtain samples from my model and compute the excess loss probabilities. That's it. So the trouble with this is that like we are going to see the relevant scenarios only a small fraction of times, only beta fraction of times. So in that sense, like the sample complexity or the sample requirement which is needed to kind of perform estimation would be growing like 1 over beta. If beta is small, compared to whatever is usually required for estimation, I will be requiring 1 over beta times that. So if, for example, beta is 1 in 100, I would be requiring 100 times more samples. In a cyber physical system, if I'm interested in a safety guarantee of beta is equal to 10 power minus 6, then I could be requiring million times more samples to perform the tail estimation. Likewise, in optimization, optimization tasks are more challenging than estimation tasks. So in that case, like I'll be kind of like even requiring like a larger constant, but the scaling would be just 1 over beta again. Like, so I'll be kind of like requiring 1,000 times or 1,000,000 times more samples, depending on the rarity. So despite this heavy sample requirement, I just want to emphasize that sample average approximation is the near universal method, because that's the only reliable method which works near universally. Now, just to have a sense of like, I kind of give the sample requirement in terms of like the complexity like 1 over beta, but just to have a sense of, have a feel for like what these numbers mean. For example, like if I'm kind of minimizing a portfolio CVAR of 100 stocks, and I kind of like want to kind of like do it within 10% relative error at the tail level of 1 in 40, beta is equal to 1 in 40. Just 1 in 40 is not so rare. Even for that, it is kind of has been estimated like that you need just like, it has been shown that you need 14 years of daily returns data. And the perils of minimizing sample averages with insufficient samples and using those conclusions have been like kind of well recorded in the literature. So despite like these shortcomings, despite this heavy sample requirement, just sample average approximation is the only method that we really and reliably have. Our goal in this talk is just like kind of to see to what extent, at what generality and to what extent we can slash this 1 over beta down all the way to 1 over beta power small o of 1. So here small o of 1 can be seen as 0, almost 0 as beta goes to 0. The small o of 1 is written with respect to beta. The easiest way to understand, the easiest but a rough approximation to what this 1 over beta power small o of 1 is polylogarithmic in 1 over beta. So I want to reduce the sample complexity from 1 over beta all the way to polylogarithmic in 1 over beta. So that's what I want, like both for estimation as well as optimization. So for what type of problems and for what type of models and what generality I can achieve it, what is the procedure that can help me achieve that? This is our goal. And this polylogarithmic requirement is also kind of like popularly referred in rare event simulation literature as log efficiency. So for people who have like for researchers who have kind of seen a lot of rare event simulation papers, the log efficiency may resonate a lot. And it's kind of nearly optimal because I'm kind of making the exponent almost zero, like the exponent of 1 over beta, the exponent, the term in the exponent, small one, I'm making it almost zero. So it's nearly optimal and it's called log efficiency. And it's kind of seen as a gold standard for variance reduction. Now, so we saw that like the most common and prominent approach is sample average approximation. And also we have a nice rich literature like which kind of explores variance reduction. So variance reduction methods there are multitudes of variance reduction methods. For example, importance sampling is a prominent method which is used in many branches of science and engineering, as well as like we have splitting, we have conditional Monte Carlo. So we have a good number of variance reduction methods. So, but this talk, since importance sampling is the most prominent, I'll just restrict myself to importance sampling here. So what is importance sampling? You want to perform a tail estimation task, which kind of has to evaluate the probability of this red region in the picture here. So I hope you can track my mouse. So the red region in this picture here. Now, if I just obtain samples of the normal distribution, I'm not going to see a lot of samples there. So importance sampling would say, why don't you change the distribution? So I change a distribution which puts a lot of mass in the regions of tail interest, and then I kind of reweigh the likelihood ratio, reweigh the samples by likelihood ratio, so that the bias is adjusted. So it's a very intuitive method, just a change of measure argument works. But the difficult task typically is in kind of coming up with a good importance sampling distribution. So we will see in more detail why that can be hard. But at the moment, if you have a good importance sampling distribution to begin with, then this is a fantastic method, fantastic variance reduction method. But as such, the task of identifying a good importance sampling distribution has been only possible, at least reliably possible only for stylized small examples. Otherwise, most of the time, the second most methods that we use typically, how in engineering as well as in many branches of sciences, we kind of have good intuition of the problem, so we kind of do some heuristics. So the sample requirement will be unknown. And finally, so we have this, what gives us hope, a ray of hope is there is this wonderful tool set developed in rare events simulation, large deviations literature, where you can engineer good importance sampling distribution, where you can engineer good variance reduction by large deviations analysis. You kind of first study how the rare event is happening, and then kind of use that to come up with a good importance sampling distribution. So with that, the gold standard of log efficiency has been shown, but so that's what gives us hope, why we can actually hope for something better. But on the other hand, it has kind of been largely only for stylized models, extremely stylized models, something like sums of independent random variables. So here in the right, I kind of show not a complete representation, but a good representation of where, when it comes to distribution tails, where the rare event simulation kind of stands. So what we have is we have beautiful algorithms for very specific models, very specific distributions, and very specific objective. So I'm not going to enter into the details of each of these algorithms, but one thing I want to register is each of these algorithms work typically only for the combination that I mentioned. So if I take one algorithm, change the underlying distribution, the algorithm will not be applicable anymore, and it may give very poor performance. So they are extremely tuned, hyper-tuned. They are hyper-tuned. They are beautiful algorithms. They are hyper-tuned to specific problems and are available only for a small class of models or problems. So, and they don't extend typically beyond something like sums of random variables. And even if I'm interested in something for example, seeing how value of an LP is large. LP is LP integer programs are all commonly used in OR. But even for such prominently used tools, so if I want to kind of study the distribution tails, I just right now, to the best of my understanding, we don't have a reliable way of approaching this. And another shortcoming is that a good performance in one particular model does not extend when the distribution or loss changes. And due to these shortcomings, so it kind of has remained only as a possibility. It's an exciting possibility. So as I mentioned, sample average approximation remains as the only reliable method. So the heuristic variance reduction is for adventurous. Like, so if I'm adventurous, I may use it. But like, what gives us hope, the variance reduction by large deviations analysis has only been limited to small problems and relies on an expert in the room, who can study the problem, come up with the large deviations and go further. So it has only remained as a possibility. So just we want to explore how much we can stretch that possibility and get this gold standard of log efficiency across a wider class of problems. So the question that we are asking here in this talk is, can we have samplers which are both efficient as well as broadly applicable? And what I want to convince you in this talk is yes, but if we ask for change of measures prescriptions completely differently from how we are used to asking, if we ask for change of measure prescriptions completely differently, then yes, we may. So the talk is structured as follows. So first I want to first bring out why finding efficient samplers, what is fundamentally difficult about the problem, why finding efficient samplers are elusive, why it is hard. And I want to make then a key observation on our proposal, and then develop the large deviations machinery, tail modeling and large deviations machinery, and then just quickly show the sampler efficiency guarantee and with some intuition of the proofs, and then conclude with some simulation experimental results. Yeah, this is the plan for the talk. If I see a question, what is R theta in your optimization problem is a question I see. It just is the return, it's a return requirement. It could be any return requirement. I haven't defined it concretely in the problem. Okay, let me move on. So the first question I'm going to address now is why efficient samplers are elusive. So here I just so the pictures can be drawn only in 2D, so I have all the pictures in 2D, but we can extend it to multiple dimensions. So here I have a loss, which is a piecewise linear loss from ReLU neural network. I have drawn the level curves of the loss. And what we have plotted is conditional excess loss samples. Given the loss samples being large, how the excess loss samples look like, that's what we have plotted. And these are samples from multivariate normal distribution. So we see that the losses are the loss samples are concentrating in these two regions, symmetrically around the interior of around the 45-degree line. And now, when I change the distribution for the same loss, when I change the distribution from multivariate normal to a variable marginal, the same Gaussian copula remains, but I just change the marginals. When I change the marginals, the points of concentration is completely changed. And when I change it to exponential marginals, again, the point of concentration completely changed. And these points of concentration are disparately different for each of these three pictures. And now if I have a problem in multiple dimensions, some 10 dimensions or 50 dimensions or 100 dimensions, you can imagine that the points of concentration, there could be exponential number of points where the conditional excess losses or samples are concentrating. And without carefully studying the problem, studying the problem, I may not actually have a good idea of where they are concentrating. If I know them, then almost half the problem is solved. But where the problems are concentrating, it's not so easy to find. So as such, the principle behind a good sampler will be, it will try to concentrate its mass at the right collection of points. So it will not put mass in the sparse regions. It will, in the circled ones I show here. So it will try to concentrate its mass at the right set of points. So one approach may be to use mixtures which have whose mode or the center is at the right set of the circled points. And then it's also important to preserve the relative levels of concentration. So a 1 point of concentration here, if you see the third panel, 1 point of concentration here could be more than the other point of concentration. So it's also important to preserve the relative levels of concentration. And all these data, so where the mass is getting concentrated and what is the profile, where it is more concentrated, where it is less concentrated, these are instance dependent in a highly non-trivial fashion. So it depends very, very intricately on the loss as well as the distribution. So this is the key source of trouble. As such, given a loss and a distribution, I immediately don't know where the excess loss samples will be concentrating. So if I have to choose an important sampler, I will try to, if I know them, I'll try to concentrate on those points, but I don't know. That's the problem. So how this has been approached is just study the model, perform large deviations analysis to propose a good alternate distribution family to sample from. First, so I kind of study the problem and then propose a good alternate family. So these families, even in elementary settings of Gaussian random variables or IID sums, they kind of have been very disparate. For example, sometimes it's appropriate to use exponential twisting. Sometimes it's appropriate to use hazard rate twisting. These are just names of different algorithms, but they kind of what I just want to kind of convey here is the families that we have to come up with for different problems are quite different. And sometimes it has to be mixtures. So it's kind of not immediate, how one would choose a good distribution family, for general problems. The second thing is, once I choose a family, for example, if I chose mixtures of Gaussians as my family, then I have to choose its parameters. So what is the mean and what is the covariance matrix I'm going to sample from? That I have to choose. So that typically is obtained by solving a quadratic program in the case of Gaussian distributions. If you kind of have, it may also sometimes have combinatorial structure. Sometimes it could become a non-convex problem. Sometimes it may involve a mixed integer program, or sometimes it may require a dynamic control problem just to find good set of parameters from which I can sample from. Once I have this, then the third step of difficulty is it should be easy to sample from those families. So all these three requirements have to be satisfied. And each time when I try to kind of try to do that for a particular problem or particular model, it becomes quite a formidable task and becomes a paper in itself. So it's now I just kind of want to move on and say, what is the difficulty? What is the bottleneck in using importance sampling in optimization? The tricky part here is when my decision changes. For example, in the left panel here in the picture, I have a linear portfolio loss with 0.2 weights on the first asset and 0.8 on the second asset. On the other hand, in the right panel, I have 0.8 in the first asset and 0.2 in the second asset. The weights are flipped. I see that just with these two different weights, the points the points of concentration are starkly different. So that is again a difficulty. So based on my decision point, I will have to use different importance sampling distributions. And for each of that, I have to set up and solve an optimization problem to get a good set of parameters and then go on and sample. So this really becomes a bottleneck, and it has kind of been so this has been observed. What is a good sampler for one decision choice is often not good for other. And that has been recorded as a key bottleneck in kind of extending the use of importance sampling to optimization. And now, what is the diagnosis of this difficulty? So I presented what is the difficulty of the problem I just hope to convey. So all the pictures were in 2 dimensions, but we can imagine what would happen in high dimensions. There could be exponential number of concentration points, and to find each one of them is kind of searching for a needle in a haystack. So our diagnosis of the difficulty is that this difficulty persists and is likely to persist as long as we kind of try to seek an explicit prescription for change of measure. Almost all the approaches in the literature try to kind of say, oh, this is my importance sampling distribution. This is what I'm going to use. I'm going to sample from this distribution. I want to write it down, or I want to kind of codify it somehow explicitly. This is my change of measure. So as long as we seek an explicit prescription for a change of measure, the difficulty will persist. This is our diagnosis. So we kind of propose to instead instead of rather than explicitly writing down the importance sampling measure, can we automatically induce it? Can we somehow induce it? So to this end, this is the key observation. So now I'm going to introduce the key idea behind our method. So, and what is our proposal? So this set of slides is probably contains the gist of what I want to convey. So here, so the key observation, so you may remember, relates to this. You may remember this picture, the 3 pictures, the 3 panels, each one of them for different distributions, and the point of concentrations are different. One in the 45-degree axis, one in the middle, it is in the axis, and in the last, it's all over the place. So we have these 3 different points of concentration. What is striking is that these concentration profiles are exactly or almost exactly replicated at lower levels of rarity. So the blue samples here are the samples of X conditioned on the loss being large, but a lower level of large. For example, you could, L of X being U could be corresponding to a 1 in 1,000 event, but L of X greater than L is a lower level, and it corresponds to 1 in a 10 event. So in this picture, what you are seeing is that blue samples, which are a lower level of rarity, occur 10 power 3 or 10 power 4 times more often than the red samples. And typically, we don't leverage this information at all. These are not so rare. They are readily available, but we never leverage this information at all. And the key observation that I kind of want to emphasize here is the tail events at different levels of rarity occur in structurally similar ways. In all the three panels, you see that the blue samples concentrate at the same regions as the red panels. And this information can be used. That's the question. So the question that we are asking here is like the approach is kind of like going to be drastically different from how it is normally pursued. So is there one transformation? So the approach like that we are taking is there one transformation which can induce each of these red profiles when applied to the less rare blue samples? So the blue samples are more readily available. They are 1,000 or 10,000 times more often seen. So when I apply a transformation, can I replicate these concentration profiles at higher levels of rarity? Is there a concentration preserving transformation? One transformation which applies for all the three problems here, or all for various groups of problems, like I just apply one transformation, and the push forward measure with respect to this transformation, can it be a good importance sampling measure? So in a cartoonish way, if I kind of want to depict like what we are trying to pursue here. So traditionally we have model 1 and we try to find good importance sampling for it. Model 2, we try to find another good importance sampling for it. Model 3, another good importance sampling for it, and so on. That's what is traditional. What we are proposing here is, can I identify a measure T? Can I identify a transformation T? I look at the transformation T, apply it to my samples, the push forward measure, the push forward density. Can it be a good importance sampling distribution? Is there a chance for that? So we have kind of translated the question from a search for a good importance sampling density to that into a search for a good importance sampling, good transformation. So that's the progress we have made. But is that possible? Like, is that even a possibility? Can there be one transformation which induces a good importance sampling distribution for n number of problems? That's not clear. It's not a given. So that's what we want to establish now. That's what we want to kind of do for the rest of the talk. Actually, what we kind of like show is a fixed elementary transformation of the samples is actually efficient. So just like this transformation here, which does not look at the distribution, which does not look at the loss samples, it just applies the transformation in this way. Like these are fixed parameters. U is like the excess loss level, probability of L of X greater than U. It's a problem parameter. And X is my sample to which I'm going to apply the transformation. And L is a suitably chosen lower level. So this L can be seen as a hyperparameter. And this kappa, the exponent is given like this. So it's a very simple to implement, like not at all a complicated transformation. And actually we show that this fixed elementary transformation of the samples is efficient for n number of problems. So just to kind of give an idea, so I apply this transformation to two different problems here. So we have the multivariate normal example, like where when I apply the blue samples here, the left panel, the transformation, I apply transformation to the blue samples. I see that the red samples are kind of like, and the blue samples have similar concentration profile. Similarly, I change the distribution, but I apply the same transformation. I see that like the blue samples and the red samples, like when after applying the transformation, kind of have identical concentration profile. They concentrate at the same places. So this is the transformation. This is the simple algorithm. So, and this is enough for a good number of problems. So what range of problems can we solve with this? That's what I'm going to address now. So the first contribution is this simple algorithm. The second contribution is we have this tail modeling and large deviations. Like, so we kind of like equipped with this observation, we just want to first understand what sorts of models have this self-similarity at different tail levels. And then we develop a unified large deviations treatment for studying those models. We propose the model class, we kind of like which captures the self-similarity. And then we do a unified large deviations treatment. And finally, we kind of like do some tail asymptotics for that. And then we can actually like show that like it kind of is broadly applicable. It extends the scope of, importantly, it's not like just being good for existing problems. It extends the scope of efficient importance sampling to various new models. It's also applicable for risk management models like the neural network, credit risk neural network example that I showed before, where you could be using sophisticated predictors. Or also it resolves the bottleneck and make importance sampling workable for optimization. So these are the primary contributions. So there is a question. Let me address that. Does this transformation depend on the loss function? I just need some basic assumptions on the loss, which are like highly non-restrictive and some basic assumptions on the distributions. Some regularity assumptions on the distribution, which I will be explaining shortly. But other than that, it does not depend on the laws at all. So this transformation, as long as the assumptions are respected, this transformation works. So in a way, like when we kind of landed in this transformation, it was fascinating to see that such a simple transformation can actually do the task for multitudes of problems. So now let me kind of go and formalize this. So how to deduce the transformation? What is the large deviations machinery which allows me to do that? That's what I'm going to develop for the rest of the talk. Any other question at this point of time? Okay. So what are the distributions? What are the tail models that we allow? Sorry? So
Dave seems to have a question.
Yes.
Dave Walker.
I the text. Yeah.
I'll just shout it out. So just try to kind of place this conceptually at a high level, like, you know, so I'm not an expert on importance sampling, but, you know, at a high level, I guess my understanding is if something has an exponential tail, if you kind of knew the exponent, then you could do the good change of measure, but you don't know the exponent is kind of the high level of that, at least is my primitive understanding. And so just to kind of place this, like, is there no past work where people just try to learn that exponent from data? Maybe there's not. I'm just trying to, because it's natural to do that, I guess.
Okay. First, thank you. Thanks for the question. First, actually, exponent, like learning the exponent for twisting, that doesn't work for just a large class of problems. It's only if I have independent sums. If I have independent sums and allied problems with similar structure, additive structure, exponential twisting can be made to work. But even when I kind of like, even that doesn't hold if my distribution is changed from light tail to heavy tail. So there is wide like kind of disparity. There is even question on like how effective exponential twisting is for difficult problems, larger problems. It has been shown to be efficient for a restricted class of problems, but we are here like kind of looking at like much larger class where exponential twisting by itself is not efficient. So learning the exponent would not help at all.
Or maybe to put the question another way, like for problems where you knew that it did have kind of an exponential tail, is what you're doing here equivalent to learning the exponent? Because again, at a high level, we say, well, if you knew it's e to the negative 10x, that's true if x is 100, it's true if x is 1,000,000. So you just got to learn the exponent somehow.
No, this doesn't do that. This doesn't do that. Okay. This doesn't learn the exponent. Yeah, it doesn't learn the exponent. It learns only, it learns the points of concentration from data and just tries to replicate it at higher levels of rarity. So it doesn't learn the exponent. There is just no, there is no explicit learning of exponent happening. It doesn't do that.
Okay.
Yeah.
Okay, thanks.
Cool. Thank you. Thank you. So now, so just to kind of like now make the, introduce the assumptions under which we are operating. So here we have, the only assumption that we make on the distribution of X is that either the distribution is regularly varying, the density is regularly varying, or if it is heavy tailed, or if it is light tailed, the logarithm is regularly varying. So what do I mean by regularly varying here? So for example, let me examine this light tailed one. So f of X, if I write down the density, it's kind of proportional to this E, within the exponent, I have this phi of X, where phi of X is like polynomial, nearly like a polynomial. So I may find sequence of constants. I may find sequence of normalizing constants, Qn divided by n, it goes to phi star. An example may kind of help it easier to understand. For example, if I have multivariate normal, I know that this phi of X function is X minus mu transpose sigma inverse X minus mu. So this is what sits in the exponent. And if I try to kind of normalize like this, phi n power half X divided by n, then it converges to this X transpose sigma inverse X. So this is an example of regular variation. Here, for example, if this phi of X, if you see, it's nearly like a polynomial. It's like a polynomial. It grows like a polynomial. So I can also have slowly varying terms multiplying, but it's nearly like a polynomial. It's approximately a polynomial. So as long as you have this polynomial structure, it's fine. This phi star, limiting phi star could be any non-parametric function. So it doesn't need to be something parametric. It can be any non-parametric function, and it somehow gives the shape of the tail. So this phi star gives the shape of the tail. In the multiple dimensions, how the shape of the dependencies are, it captures that. So what all types of common models that we kind of like use in risk management or in OR, like which kind of like fit this description. So just like take any distribution that we commonly use, which kind of like has support all the way to infinity, not the bounded ones, but support all the way to infinity. For example, normal, multivariate T, copula densities like Archimedean copula, extreme value copula, or elliptical densities, exponential family, certain log concave densities, all of them, whether light or heavy tail, if you're using light or heavy tail marginal, doesn't matter. All of them, most of what we use kind of satisfy this assumption. So why? Because like we are not making a parametric assumption. We are assuming only regularity. We are not making a parametric assumption, and many of them actually fit the description. And these model class are rich enough to include models with hidden regular variation, as well as some residual tail dependencies. Now, what does this assumption buy me? So once I have this assumption in place, it kind of like immediately gives me that X suitably scaled satisfies a large deviations principle. So probability of X lying in some tail set can be kind of like approximated well by this large deviations principle. So what is the intuition behind this? It's simple. Like, so I have a set A here, and I just want to kind of like know its probability. So what I do is I kind of like write it in terms of like some union over small balls, like balls, and then try to evaluate the probability of each ball. And within each ball, it can be approximated by the density times the volume. So the probability will be proportional to summations over the center of the balls, e power minus n, this phi star z. Like, why phi star z? Because f, q, and z can be approximated by e power minus n phi star z. That's what the assumption gives me. So I have this e power minus n phi star z. So when I'm adding exponents with different rates, the one with the largest rate is going to dominate. For example, if I'm adding e power minus 2n plus e power minus phi n, e power minus 2n is going to dominate. So with that logic here, only the infimum will stand out. The others can be kind of safely like kind of like in the, if I'm just trying to understand the exponent, the others can be ignored. Only the infimum of this phi star will stand out. And that phi star z is what I call as phi star a here. So the infimum over the phi star z is what I call as phi star a here. So this is how the large deviations principle comes out from the assumptions. Now, if I have a bigger tail set later in the tails, but with similar structure, then what happens is like it can be kind of like approximated by a multiple of the smaller set, and just the probability will be just square of this earlier probability. So that also comes from the large deviations principle. So this is the base for the self-similarity. So the later tail sets, actually their probability can be inferred from the earlier tails as well. Now, so given the distribution of the assumptions, like the assumptions on the distribution, I just want to move on to the assumptions on the loss. So that was the question. What type of losses do I consider? So we just require the losses to be asymptotically homogeneous. So I have like the loss grows like L of nx divided by n power rho when I normalize. The loss grows linearly or quadratically or like with some exponent rho, it grows. I just require them to be asymptotically homogeneous, not even exactly homogeneous. And the resulting, the L star, the limiting L star is going to give the shape of the level curves of the loss. And they can be like arbitrary non-parametric function again. So if we try to kind of like write down common models used in OR or risk management, again, piecewise linear quadratic functions or optimal value of LP linear program, mixed integer linear program with random coefficients, or if I kind of like look at ReLU neural network, all of them kind of satisfy these assumptions. It's again a generic assumption. All these two assumptions just specify regularity, nothing more. Like the regularity as we go deeper and deeper in the tails, they don't impose a very specific structure other than this regularity. It's entirely non-parametric and very expressive. Now, if you want to kind of see how does the large deviations even happen, like what is the mechanics, like how does this tail even happen? How does the excess loss even happen? That also gets easy to read off from the large deviations principle. So how that happens is like, so I can write down this probability of L of x greater than u as exponent of the rate at which this decays can be written in terms of two things. One is TU, which is related to the Q, the normalizing constant. It's the rate at which it's the kind of like the growth rate. And phi star is the constant. Like it's kind of like the multiple. Like in an exponential distribution, we have the rate of the exponential distribution. This phi star is playing that role. And what is this x? This x is nothing but the cheapest way. It captures the cheapest way in which the rare event is happening. So for example, here you have the two things which are determining the rare events happening. One is phi star and another is L star. The limits of L star, you try to kind of hit it from below with the contours of phi star. And that's what is the argument problem, the minimization problem is. And the earliest point in which you hit the level sets with the contours of the distribution phi star, they are the points where you will see concentration happening. So if you kind of like map this points x to what happens pre-limit in the data, in the sample data, you see the concentrations are reflected, the points of concentrations are reflected by these X points. Now, if I kind of move on, and if I change the distribution, then to kind of actually like the points X capture the points of concentration. So here, let me go back to this normal example. Here I have two X's, so these are the 2 points of concentration. Now, what amounts to the self-similarity? So I'm here looking at the level sets of lower rarity, and I see that the points at which the level sets are the level sets of the distribution phi star, at which it intersects the level sets of L star, are congruent at both the higher and lower levels of rarity. The X's and O's are congruent to each other. Why is that happening? That is happening because L star and phi star are homogeneous functions. Like the limits are homogeneous functions. So the points of concentration at the upper level can be read off from the points of concentration at the lower level and vice versa. So this is what allows us to develop the transformation, if you think about it, right? So the X's are at higher levels of rarity and the O's are at lower levels of rarity. Now, due to the homogeneity, we have this congruence between X and O. And the same principle applies even if I kind of move from one distribution to another distribution. The points of concentration are different, but still the congruency is maintained. Now, given this, the question just amounts to we wanted to find a transformation which preserves the concentration of the points. So the question then amounts to, can we find a rate preserving transformation which kind of maps every possible points of concentration on the x-axis, on this lower level, to every points of concentration on the upper level. So regardless of the problem, can I have a map which achieves that? That's what the question amounts to. So regardless of the underlying problem, if my distributions are different, I can have different points of concentration. But if every point in the lower contour can be mapped seamlessly to every point in the upper contour, then I kind of have this concentration preserving happening to intuitively to some extent at least. So is it how do we kind of find such a point of concentration? Just use the homogeneity, and if map X, if the map says that it takes X and transforms it to X times U by L power some this exponent, that is what is if I kind of analyze the 2 level curves, this is what it would come out to. How I can map the lower level optimum points to higher level optimal points. This is what the map that will make it happen. And this is purely coming from the homogeneity of phi star and L star. And this is what I can get from the limit picture. From the limit picture, I can go back to the pre-limit picture and deduce this transformation. And this is the transformation we use. So just to give this intuition behind this all-important transformation that we propose, from this work's point of view, this is an important transformation. So just to give intuition behind that, it's simple. U is the problem parameter. I want to kind of evaluate at the rarity U, the level sets at level U. And SL is a lower level of rarity. And I'm going to kind of multiply. I'm going to stretch every component, but I'm going to stretch them differently by this exponent. That extent of stretch is determined by this exponent kappa. So what does the kappa do? What kappa does can be understood from this picture. So what it does is, in the blue samples, if both the components are large, then it makes both the components high. If on the other hand, if you go to the third panel, you see that only one component, x1 is large, but x2 is not large. In that case, it only stretches x1 to a larger value of x1. It doesn't stretch x2 to larger value of x2. It just keeps it as it is. So the role of kappa is to actually act as a modulator on you look at the sample and then see how far they should be stretched. It's a simple stretch, but each components are stretched differently based on how large they already are. So this is what you can see that the concentration of kappa is at 1,1. Both the kappa are both the components are being stretched in the left panel, also in the middle panel, but on the right panel, only one of the components is stretched, the other component is not stretched at all. So this is what allows you to kind of preserve the concentration. And now, maybe in the interest of time, I'll just skip the mechanics of this. But then what does the proposed sampler look like? So the proposed sampler just is a simple implementation of this transformation. So what I do is I obtain n samples from the original distribution. No fancy sampling. I just obtain n samples from the original distribution and I apply this transformation. That's it. So the L is the hyperparameter. U is a problem parameter. It's coming from the problem itself. The level sets at which I want to compute the rarity probability, that gives the U. L is my hyperparameter. So that alone needs to be chosen. But other than that, everything else is frozen. And just like once you determine the once you kind of like get the samples, important samples, calculate the likelihood ratio. The calculating the likelihood ratio is just a simple application of Jacobian. Like, so since we are transforming samples, like if we just go to like, undergrad, like math, like, so the Jacobian like will come up, and that's what the likelihood is. And then finally, like I just like return the likelihood weighted estimators. The algorithm is quite simple and it can be reliably applied across multitudes of problems. And what we can show in terms of proper like guarantee is that like, so for the estimation of probability of L of x greater than U, if I can take L to be significantly smaller than U, that means I'm kind of getting a lot of stretch. I'm making a big stretch, but in the way that we talked about, then the proposed sampler offers like log efficient, in other words, like asymptotically optimal variance reduction. What do we mean by that? Without the importance sampling, you would have 1 over PU, where PU is the rarity. PU is the probability of L of x greater than U. That's the rarity in the problem. So you will have 1 over PU without importance sampling. But with the proposed sampler, it will become very exponentially smaller. It will become 1 over PU per small over 1. The easiest way, as I mentioned before, is to interpret it as polylogarithmic in PU. Now, numerically, okay, theoretically, like, okay, we can show the best, like the gold standard at least. Again, and at the complete generality, like we considered. It's not all possible problems, but it's quite general, like at a level of generality that we haven't seen before. It works. And when it comes to numerical results, we see quite good performance. So these are like, so here I kind of try to compute the probability of excess loss in a portfolio with 3,000 loans. And the default this is like, what is the loss here? The default probability is the loss modeled by neural network. And I kind of like, without the important, I kind of plot the variance without importance sampling and variance with importance sampling. And we see that like, as we kind of like make the problem rarer and rarer, the extent of variance reduction increases by a factor of 100 to 10,000. And the variance reduction, we observe that it persists across experiments too. And you may be concerned, like, so what if there is this one parameter which needs to be chosen. What if the variance is too sensitive to it? Actually, like we show that, like, as long as your U over L is very small, U over L is very large or L over U is very small, as long as L is only a small fraction of U, you get good amounts of variance reduction. So it's not sensitive at all. That's what we show with the theorem. But here, like in terms of like experiments too, we observe that like when you plot against L, the variance, we do not see a huge sensitivity at all. It's relatively flat. So it's not too sensitive to the choice of L. So finding a good choice of L is relatively quick. And if you combine the efforts of like kind of finding a good choice of L as well as like kind of like the overall like sample requirement, if you combine like, so it kind of like outright beats the benchmark like kind of method. In a benchmark example, like, so here we have considered like PERT network problem, which is a standard problem in Rubinson and Crusoe's tutorial. We see that like the combined effort, the combined number of samples that is needed for our important sampler is again exponentially smaller than just applying merely a cross entropy method without like kind of carefully choosing the distribution family. So does this benefit carry over to optimization? We show that like, since it's a black box sample, it doesn't look at the loss seriously. It doesn't look at the sample seriously. As long as the regularity conditions are satisfied, it works. And we see that the benefits carry over to optimization too. So again, like we can prove a result which says that with the important sampling, you only need polylogarithmic amount of like in 1 over beta, in contrast to 1 over beta without importance sampling. And again, numerically, we kind of see that like as we go deeper and deeper in the tails, when I'm trying to kind of minimize here, like this is an example where like I kind of try to minimize portfolio risk subject in for a 15 assets problem. And I see that like as I go deeper and deeper in the tails, like so I kind of start getting variance reduction up to a factor of like 25 times variance reduction. So the naive sampler without any important sampling has 25 times more. And it's conveniently workable with optimization. So just to summarize, like, so I think I'm kind of like close to time. Like, so just to summarize, so we proposed a scalable alternative for sample average approximation. That was the goal. Like, so when it comes to all these tail problems, regardless of how much whatsoever we have regarding important sampling, people just like, it's like practitioners as well as like kind of like people outside applied probability, everyone prefers to use sample average approximation because that's the only reliable method. So to obtain, and no variance reduction, I'm fine. I'll just devote a lot of samples. But we have had this interesting possibility. In applied probability, we have had this interesting possibility of leveraging large deviations to carefully engineer variance reduction. The only trouble has been, it was not scalable. It didn't extend to a wide class of problems. So in a sense, like, so it was like kind of going through the kind of difficult pipeline of step 1, step 2, and step 3. which was like kind of quite cumbersome and difficult, not scalable for difficult problems. So what we kind of have proposed to do in a rough sense, like in this work, is to kind of automate that whole procedure. Everything again informed by large deviations, but automate that whole procedure. We don't need any of that. Just the transformation will do the business. So the question for explicit search for alternate distribution kind of get turned into search for a transformation, which kind of like is again distribution oblivious, problem oblivious, and so on. But it kind of like does the right measure indection. And also like kind of like hopefully like with this like we kind of like make importance sampling like kind of scalable for optimization problems involving chance constraints or CVAR. It's very often we find problems involving CVAR and chance constraints, but the most go-to method has been again sample average approximation. The use of importance sampling has not been like kind of like quite scalable. We hope like somehow like this is an initial step towards bridging that gap. With this, I thank you for the attention, and thanks a lot for the opportunity. Thanks a lot.
Right. Thank you very much, Karthyek. So we have some time for a Q&A. So does anyone have a question?
So maybe if no one else has a question, I'll kind of re-ask what I asked before, just for my own understanding. So I guess if applied to one of the settings we already understood, like sums or whatnot,
Yes.
is this implicitly learning the exponent or no?
Okay.
Because it would seem consistent with I'm just trying to understand. It seems consistent with that concept, kind of.
Yes. Yes. It will implicitly kind of like learn the exponent based on how the exponent was kind of manifest. The exponent itself was not of interest to me. The exponent was manifest in a certain way at lower level of rarity. So it will learn that phenomenon alone. Like, so it doesn't learn the exponent explicitly. It just like learns the phenomenon which leads to the concentration and just replicates the concentration. If it tries to learn the exponent, then it will become not scalable. That would be the difficulty. So it would implicitly kind of learn the exponent. That's my answer to your question.
So I guess like, what do I wish to say? If instead of focusing on how the rare event happened, if you knew roughly just the functional form of the probability of the rare event, just broadly in a linear, anything, say, it's whatever, a polynomial times e to a negative quadratic or whatever it is. Like, I still remain confused about why you couldn't just learn those parameters for smaller values of x, or like, why is that not an alternative way to look at what you're saying in some sense?
Yes, I think, yes, one can do that. Yes, one can do that.
Would the same math kind of work where you'd say, well, as long as the number of parameters is not so huge, then when x is small, you could learn those parameters. And then as long as the uncertainty in learning those parameters does not dominate the rare event itself, you're okay.
Yes, that is a legitimate suggestion. Thank you. So what I would say perhaps is like, yes, if I know this is the parametric family that I need to use. For example, sometimes exponential twisting works. If I know, and I also know, if I have an understanding of how the parameters are related to how the rarity is happening in lower levels. If I have an understanding of this, then yes, I can learn the parameters. And that's what happens typically like when we have multivariate normal distribution. That specific case, it has been studied very well. But when I start moving beyond like kind of multivariate normal distribution, so how the points are concentrating, what would be a good parametric family which approximates it, none of that has been very clear. So here I would kind of probably like to say like, so this kind of like is complementary to another, actually with a similar motivation. Henry Lamb, like, and his co-authors, like, have been like kind of like doing cool work again in learning the parameters, right? Like, so, and it's learning the parameters will give the best possible variance reduction. This is a rough and ready tool where you don't have to learn the parameters, because learning the parameters at the end of the day, like kind of like may not be the most useful thing. But if you learn the parameters, like then it kind of like gives excellent variance reduction, but it is conditioned on knowing that you know the parametric family.
That makes sense.
What is a good parametric family? So that is not immediate often.
Okay, so the point here is you do not need to know, you're showing you can implement a change of measure there without needing to know the parametric family explicitly.
Yes. And what is for one distribution choice, like one parametric family, if I change the distribution choice, it becomes completely different. Now it is that knowledge. What works for a problem is not there. That's what is the fundamental bottleneck. Not the learning the parameters is not the big deal, but like even what is a good parameter family, even that is like kind of not clear for sophisticated problems.
No, it makes sense. Okay, that I think I understand now. Very good. Thank you.
I can ask a question if that's okay.
Okay, thank you.
So Karthik, I have a question for you. I mean, it looks like what you're saying is that you have this non-rare data that you push further in the tails, and then you estimate the tail events, tail performance measures, you optimize on the tail performance measures.
Yes.
I mean, you could do the other thing as well. You can just estimate the non-rare performance measure first, and then push the performance measure towards the tail. At least for optimization, that would work, right? Because there's a lot of uniformity you're assuming in the structure. So you optimize the non-rare problem, and that's probably a pretty good optimizer for the tail problem too.
Yes. Yes. I think that's a legit suggestion. Very, very nice suggestion too. Thank you. So what you are saying is I look at, if I understand, just to rephrase, if I understand correctly. So I take a look at L of X itself, the L of X itself, instead of looking at the distribution of X, like I just take a look at L of X itself and then try to learn its behavior at lower level and then push it to higher levels of rarity. Is that right?
Yeah, I mean, push the performance measure to the, learn that at the lower level and push the performance measure to the, multiply that with the right factor.
Yes, but for that, wouldn't I need if I want to do importance sampling, like, so if you are talking about some extreme value estimation statistics, that's a different story. But here, if you want to do importance sampling, for that, I would need the distribution of L of X, which is what is complicated. Like most of the time I'm engaged in this exercise just because I don't know the L of X distribution. But to implement the likelihood, I need to know the L of X, right? The distribution of L of X.
So it would not be straightforward.
That is the problem, actually. At the end of the day, if I know the distribution of L of X, there is nothing to be done.
All right.
We have time for one more question. So, question, Karthik, about the kappa factor. So that doesn't depend on any parameter or any information about the distribution. So that's a universal function.
Yes. So in a sense, I wouldn't kind of like I kind of would want to be not say universal, because that's kind of like a huge word here. So it is universal for the if the loss assumption is satisfied and the distribution is satisfied, then this kappa factor is universal within that class. But that is still kind of like a smaller class compared to the universality of like sample average approximation. Like, so sample average approximation, just like as long as I have finite variance, it's universally applicable. But this kappa that we show is this kappa I show here. Just one minute, sorry. Yes, this kappa factor does not depend on the loss, does not depend on the specificities of the distribution. It is universal within the class. And that is what we believe. Again, like, it may not offer the best possible variance reduction that you can get by learning the parameters, as David was pointing out, but it gives good variance reduction for me to go ahead. Like the universality of the application is what we are pushing here, rather than getting the best possible variance reduction.
Okay, and the norm here itself is just norm one, the norm of X. So that's
so the norm. That is this kappa. I didn't go through the details. Kappa is a vector. So the norm of X would be component-wise norm. So logarithm applied to component-wise. Like, yeah.
Thanks.
So that's how you get how large they are in different components. So kappa is a vector. Thank you.
So related to that, I see that there are more than one choice of T and kappa.
Yes,
right?
that's
Yes.
a very good question, which I kind of like didn't have time to address. So we actually show that the choice of T will have to be somewhat like this. We show that like it has to be somewhat like this for it to be useful, like in the way that we propose. For it to be useful in that way, it has to be of this form. But then the choice of kappa alone can have some degree of freedom. Even in our problems, we kind of like, there are certain kappas which are convenient for optimization because it preserves the convexity. So just for those purposes, we use those different kappas. So there are multiple choices of kappa which can give the good performance. But the choice of transformation is kind of almost unique. Like it's not exactly unique, but it's almost unique. It has to be of this form. It cannot be anything else. But kappa, we have a little bit of leeway. Any kappa which satisfies this convergence would kind of like allow me to kind of induce the same T. Like, so in that sense, so the T, if you see here in the top, like the T, if you see in the top, it depends on some distribution parameters. So here the kappa, the choice of kappa that we kind of make, as long as it kind of like induces the distribution parameters properly, we are fine. And there are multiple kappas which can do that. But the T choice is essentially unique.
Let's see. Great.
Other than kappa.
So Dave seems to have a question.
So maybe following up on Sandeep's question, like if you just learned what's the probability the loss is at least 100, and you learn the probability the loss is at least 1,000.
Yes.
Let's say you learn those two things.
Yes.
Is the thought then that by the kind of asymptotic homogeneity or self-similarity kind of concept, then you don't need to know the parameters of the functional form. That would already be enough then to know a million, a billion, a zillion, etc. Because it maybe, I don't know, Sandeep, if somehow that was implicit in the question you were asking, is that why do a change of measure at all? You just kind of could roughly learn how the tail relates at subsequent large values, and then do your assumptions imply that would give you the whole thing then?
Yes. Thank you for the question.
Yeah,
sorry.
No, I was just going to say that just puts what I was trying to say much better, but that's correct.
Okay.
Yeah, okay.
Because then there's no important, you don't need, when you say Karthyek, but you need to know the distribution, I'd say you don't need to know anything. All you need are those two tail points where you never need to care for learning more than the probability that it exceeds 1,000, and then you would have the whole story, right?
Yeah, fair enough. Shall I maybe attempt to answer that question? So, like
or I guess the only point is I don't think the answer, but then you need to learn the loss distribution. I don't find that compelling, because you just need to learn 2 points in the loss distribution tail for X that are not that big, and then you implicitly extrapolate the pattern because you're assuming. I mean, if one interpretation of this asymptotic structure is that the loss tail is extrapolatable, whatever that kind of means, then I don't find it compelling to say yes, but then you need to learn the loss distribution, so it's complicated. Surely from data, you can learn those 2 tail points of the loss distribution, I guess, right?
Yes. Indeed, that is correct. What you're saying is right. It depends on my objective. Given a model, if I like what you kind of like mentioned is like what extreme value theory statisticians have been like kind of like doing for decades, and it has been quite effective. But the purposes are different. So if you want to learn something from data, a univariate loss, if you just want to learn a univariate loss, like the tails of univariate loss from like the data, then it works fine. What you mentioned, yes, learning the kind of 2 points or some set of points will allow me to extrapolate to 1 in a million level, 1 in a billion level. That's correct. That's statistics. And it kind of like allows me to estimate with a huge bias if there is a huge bias. Like, so they are based on this extreme value limit theories, and there will be the amount of error that I'm suffering here. So for example, the basis of the extrapolation that you mentioned will be this formula. Here, this is the formula for the basis for the extrapolation. The amount of error suffered by this approximation is just not at all clear.
Well,
and that's where
I would only push back in saying that I don't see why it's any more or less clear than whatever's hidden in the little o of TU. In that, I mean...
The little o of TU is the problem. That's exactly what I'm saying. The little o of TU is hiding a lot of things which would have to be ignored if you are doing a straight extrapolation. But what importance sampling allows you is, there is no approximation error. It allows you to kind of like do up to a Monte Carlo approximation error. Like so, but there is no extra bias. If you want to calculate X within epsilon precision, it allows you to do that.
But if we took your approach and wanted to, and I don't know if this was on slides or not, get exact quantified theoretical interval guarantees, whatever that would mean, like confidence, I don't know what the exact theoretical quantitative bound would be. To get precise quantitative bounds out of your approach, do you run into the same issue or no?
No, okay. No, the reason is because the problem that we are tackling at a higher level is an easier problem compared to just tail estimation from data. So the problem here we are tackling assumes you have the distribution. So if you assume the distribution, then it's only a Monte Carlo estimation problem. On the other hand, what you're saying is like, given just data points, no distributional assumption, so you kind of want to estimate the tails. That's a different problem. That's a statistics problem. And the most useful way until now, the prominent way has been what you just said, extrapolate based on tails. It works for univariate. Multivariate, it starts suffering, but univariate, at least it works. But that is statistics, and there will be a huge bias. On the other hand, given a model here, I'm considering easier problem, easier but yet challenging in a different way. The problem is relatively easier to what you are saying, because here I'm considering given a model, given a distribution, I want to estimate. That is far different and far easier compared to not knowing the distribution I want to estimate.
So sorry, I thought you want to optimize, or what do you mean you want to estimate?
So I want to estimate some quantities, or I want to optimize, but I just want to kind of like, I'm given the distribution. So that's the difference between what you kind of like, so what you propose to do and what I am doing. The difference is in the goal. The goal for you is to estimate from data. For me, the goal is to estimate given a model. So the bigger difficulty, which is how do you know the model has been taken out of the equation for us? That's why you can estimate it to arbitrarily.
I mean, I somehow in my mind, I cannot make concrete the two universes you're talking about, even though it sounds very appealing. I guess that one is without the model and one is the tail from the data. But that's just on me. I mean, this is all very interesting. It's just, I know you and I talked about this before. It always seemed mysterious to me that you need to know the exponent to do the thing, and it never made much sense, even in some of these simple queuing studies. So this is all very nice, but I remain unclear in my own head. Okay, let me ask my question in yet another way. So in your main results, you talk about something being asymptotically efficient or log efficient, right?
Yes.
In your paper, do you actually have literal quantitative error bound?
No, we don't have a quantitative error bound.
To get a literal quantitative error bound, would you run into the same issue we're talking about now about, well, there's this little o and I don't know, or no?
Yeah, the little o will certainly come up when I kind of want to get a little quantitative bound. It will not be but the point is the following, like it's only a variance bound. It's not a problem. Like, so my estimate doesn't suffer from the small o of TU problem. Only my analysis of what the variance of the estimator suffers from. On the other hand, in statistics, in extreme value theory, the estimate itself will suffer because you are considering a harder problem. There, the estimate itself will suffer from small o of TU. On the other hand, here my problem is given. I know everything clean about the problem. I just want to compute something numerically to high precision. And that I can do. Small o of TU will not create an issue. Only the variance will carry the small o of TU. The real question you should probably be like, the next question probably you may be asking is, you are assuming a model, but distribution. How do I know the distribution? Like, so that's probably like the question, right? Like that's then goes to extreme value theory. Like given just data, how can you say the distribution? But that's a different question.
Okay, so wait, so you're saying for the linear program here, you don't have to learn the distribution of the coefficients from samples. You're given that written down somehow.
Okay, I know the distribution of X from Oracle queries. It can be written down or it can be Oracle queries. But the important sampling distribution, I don't know. What is a good important sampling distribution? I don't know. That's what I'm finding.
From Oracle queries, these are not sample oracles. This is like input a value, get the density.
Yes, exactly.
I know we've talked about this before when I was reading this paper originally. Okay. Now,
yeah, so this is an easier problem in a way.
So is there a literature? Have you thought carefully about, are there negative results? When you say this is an easier problem, how formally is that understood? Or clearly it sounds easier that you have access to the density, but is there any kind of impossibility results, et cetera, in which it's really formally understood that you're gaining something by having access to the density? Beyond it, it certainly seems that way.
I think like starting from data, you will suffer. There is inevitably like we will suffer the same bottlenecks extreme value theory folks would suffer. But having the density, is there a proper complexity study? No, at the moment, because to my understanding, like experts have not been seeing this as the same problem. It's fair to kind of start seeing them as similar problems, but they don't see it as same problem because here you know the model, you know the distribution, there is no statistical learning happening. So I don't even compare. That's what the approach has been until now. So like such a complexity study is not there. And what I can say certainly is if I know the distribution, then there is the usual Monte Carlo's complexity, the usual, the 1 over epsilon squared. That applies all the time. There is just no need to kind of worry further about it. Like, so if you know the distribution, the standard Monte Carlo sample average approximation, 1 over epsilon squared, that applies all the time. Variance reduction can make the 1 over beta. So that's what I initially said. The multiplying 1 over beta, the effect of this 1 over beta is what can be mitigated by variance reduction. So 1 over beta can be made to 1 over beta power small, polylogarithmic in 1 over beta. That's what can variance reduction give you. But people haven't seen these two in the same vein just because that's a far harder problem. It's a statistic problem because you are learning from data. And even that in multiple dimensions, it becomes a huge mess. Like, so to learn in 10 dimensions or 100 dimensions, like the multidimensional, how the tails are all correlated, it becomes a huge difficulty. Like, so the difficulties of kind of like handling it just purely from data is not known.
Okay, that makes sense. Thank you.
This is a simulation problem at the end of the day. This is the Monte Carlo simulation problem. If you want to bracket it, and if that bracketing may help, it may not be ideal to bracket. I agree with you. But if you want to bracket it and if it may help, you may think of it as a Monte Carlo simulation problem, that as a statistics problem.
Thank you.
But it's fair to start thinking of them together in the same way.
I guess everyone else is left. That's fair. Then I would ask a few more just specific questions for my own curiosity, which are not these big philosophical questions, unless Changhan, you're the expert. You got anything to ask? Otherwise, yeah, I'll ask something about linear programs specifically.
Oh, so you're asking if I have other questions?
I mean, have you thought? I mean, so in all these kind of complicated situations where, like, your work with BERT or whatnot, have you thought about what would it mean to ask how you would do that from data? What does it mean?
So, well, I guess, yeah. So the short answer is that we haven't pushed it that in any serious way.
That's
but that is actually, but that's absolutely a important question, I think. So yeah.
So Karthyek, then I would ask the following just specific question about how this applies to linear programs, because I'm just curious. So if you're looking at rare events in a linear program, just broadly, is it roughly always going to occur at one of the vertices? Is it like there's some special vertex, which is like the rare event vertex, or can it actually not concentrate in that way?
So, okay, thank you. I think if I didn't kind of fully cover like the assumptions on linear program, if, for example, the coefficients of the linear program are random, but the polytope is, let's say, fixed, then certainly there will be a special vertex. in which the rare event will continue to happen.
Because I guess if that's true, then that makes it a lot easier of a learning or of a problem, I guess, right?
Yes.
Does your method, because I can imagine some methods for studying rare events in linear programs are going to have, if you really parse out the method carefully, the runtime will depend on the number of vertices, where you would say which cone or which vertex, or is the thought you just learn by solving the LP what's the special vertex? You just kind of...
Yes, I think this is a very legitimate suggestion, very valid suggestion, and I think it will work as long as the LP has some sanity structure, like it will work. And I think it is doable. Like what I can do is I can take the LP and then kind of try to see like it simulate its values and see like how it is taking at lower levels of rarity.
Good. So does either your work or other work? So, okay, I know what assumption you want there. It would be a non-degeneracy assumption in either the primal or the dual. Because, right, if you have degeneracy, then you have this bizarro, you're right on the boundary, and then you can really run into trouble when you're trying to guess what's the good vertex, because there will be a handful of good vertices.
Yes.
Does your work or like Jose's work from a little while ago make any kind of degeneracy assumption?
I think like, okay, my understanding is like, we haven't like tried linear programming a lot, particularly like because in a way like the vocabulary for talking about tails, like so in rare event simulation literature, if you see, there are two themes. You may see two themes. One is this, where the Kramer's theorem type of large deviations, where the number of random variables is increasing to infinity and there is a Markov structure or additive structure, that is studied a lot. And also fixed number of random variables, but the tail is taken large. So LP value becoming large will fall in that category. And that category has not been like kind of like studied a lot. One, because the large deviations for it was also not available. And the intuition that you mentioned, like there is a special vertex at which the rarity will kind of like, there is a special rare event vertex. So that the self-similarity, even that was not crystallized at all before. So in a way, like hopefully the self-similarity, like, so the contribution here we are making is not only the importance sampling, but also the self-similar tail modeling, which can be used in multitude of purposes. Like, so for example, we can just take your suggestion now and see if there is a special vertex, learn the special vertex and kind of keep using that for linear program. None of that has been observed before because the self-similarity in how the rare event is manifesting has not been understood before from a large deviation.
But okay, now I'll push back just because I'd be surprised. Are you really telling me that in all these thousands of papers in the stochastic optimization community, it is nowhere implicit where they look at like stochastic programs, they're obsessed with them, right?
Yes.
Really?
Yes.
It's not implicit
really, yeah.
somewhere that it like settles down on, because they're not looking at rare events, I guess. They're just looking at CLT scaling, I guess.
I think sampling has, okay. I think sampling has not been the most important consideration for them. So in a sense, of course, like for a tail event, like, so they actually chance constraint programs like kind of populate like a lot. Like, so they are often written, like many problems are formulated as chance constraints. So it's not that they are not thinking about rarity. They think about rarity, but the most reliable ways in which for them they to approach is to kind of like have some nice like Gaussian assumptions and then like kind of have a quadratic kind of like translated to quadratic, or like kind of have just scenario approximation. I just sample a bunch of samples and do a Monte Carlo averaging. Variance reduction, some people have thought. So for example, Tito Home de Mello, he has written a very nice paper.
Okay.
Yeah, he has written a very nice paper on how one may use importance sampling for a very special structured chance constraint problem. And recently I visited like kind of like Prof. Shapiro was mentioning. So he met like, and then said like, he had thought a lot about importance sampling.
Where did you meet Shapiro?
So I visited Georgia Tech and gave a talk.
Recently?
Yeah, last year, November.
Oh, okay.
After the Informs.
Great, I see. Okay, cool.
After the Informs. So just after the Informs.
Yeah.
So he kind of told me that he was not there for the talk, but he later, when he was meeting, he was telling me that like he had thought a lot about like making importance sampling work for optimization. And it like he even has a paper, like Nemirovsky and Shapiro in one of their papers, they say the idea of like making importance sampling work for optimization is such a nonsensical thing. it will be very hard. Like, so he kind of said that like it's kind of quite hard. Like, so they found it like kind of.
Okay, you should put that quote. You should quote that in your papers, right? That's a nice. That's always a nice touch when someone quotes and says something's hard, and then you do it, right? That's
Yeah. I think that okay in a way, like to be very honest, I think their quote also kind of talks about dimensions. Like they were talking about 100 dimensions, 1,000 dimensions. So one of the questions that we actually really still kind of have to figure out is, does this extend to high dimensions, right? Like, so the variance reduction, does it robustly extend to high dimensions? Because in high dimensions, the volume is quite huge. Like, am I placing points correctly with the transformation? There may be subtleties. So there may be fairness to the quote. Like, so I don't have the courage to kind of like.
That's fair.
But,
yeah, that's I understand. Yeah, that
but it does work very well for linear programs and so on. Like, but not like 1,000
But I guess
dimensions.
it's interesting to ask then. So for your framework, just as is, forget trying to find the vertex or whatever, even though presumably that should be showable without too much work, I would guess. That might suggest that LP should be way, 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 way easier than like other convex programs which don't have this discrete vertex structure somehow, right?
True.
Have you thought to look into that? That somehow.
No, we haven't. Like now that you mentioned, like I'm seriously inclined. Like, thanks a lot. Like, so we never kind of characterize the self-similarity of the optimal solution itself. But that's what you are saying, and that's a very, very.
For LP, it literally just collapses at some point almost. It's not just self-similar. It becomes, very strong, some much stronger notion of self-similarity, even where it's just.
Yes, it collapses. It will collapse. Yeah, exactly. But the collapsing is happening because of self-similar. But yeah, you are right. It will collapse.
But for these other convex programs, I don't think it doesn't have to. I mean, I'm not an expert, but I don't think
yes.
It does.
But I think I still can prove the set of arguments will kind of like remain the same. That I still can prove. Like the set of arguments, but there could be many. There could be infinite, but they could be still like, I think there will be some convergence. We can show that.
Sure. No, I believe it. That's cool. That's cool. All right. Well, that's all pretty cool.